Hello, everyone. My name is David Cyncynates. I'm a postdoc over at the University of Washington in Seattle, and I'll be starting a postdoc over at the ICTP in Trieste in the fall. Today, I have the pleasure to talk to you about some work with my collaborator, Olivier Simon. He's a postdoc over at Princeton University. Since ancient times, humans have been uncovering the laws of nature by discovering new long-range forces. This began with the ancient Greeks, who would rub amber with animal fur and find that the amber would be able to push small objects around at a distance. This culminated in the discovery of electromagnetism in the mid-1800s. Also in the mid-1800s, astronomers observed the anomalous precession of the perihelion of Mercury. This led astronomers and physicists to hypothesize new planets and new laws of nature to explain this observation. And in the early 20th century, Einstein invented general relativity, explaining the precession of the perihelion of Mercury, but also ushering in an era of precision cosmology. Today, we know because of general relativity that the universe is not just composed of atoms, but also of two unknown substances, dark matter and dark energy, each of which might mediate a new long-range interaction themselves. On the theoretical side, attempts to unify the forces of nature have also led to the prediction of new long-range interactions. Famously, Kaluza-Klein theory, which attempts to unify general relativity with electromagnetism by positing a new compact extra dimension, leads to the emergence of the radion, the particle corresponding to the radius of this extra dimension. This radion would mediate a long-range force of gravitational strength over infinite range, which is constrained, rather ruled out. But the modern version of these extra-dimensional theories, string theory, leads to potentially many such scalar particles, which can mediate long-range interactions that are not ruled out. And so both on the observational and theoretical side, we have many reasons to expect that new forces might pave the way towards observations of physics beyond the standard model. Now, the way that we think about these new forces from a particle physics perspective is as the exchange of a scalar boson between standard model degrees of freedom. So here, the solid lines are standard model particles, and the dashed line is the scalar field. Upon integrating out the scalar field, we're left with a Yukawa potential between standard model particles with two parameters, the strength, alpha 5, and the range given by 1 over the mass of the scalar field. Historically, there are a number of ways that we search for these new forces, the oldest of which are tests of the equivalence principle, which look for the difference between the inertial and gravitational mass of test masses. These days, we would interpret violations of the equivalence principle as the existence of a new force-carrying particle, but these tests go back a long way. For instance, some of the first tests of the equivalence principle were performed by Galileo when he dropped test masses off of the side of the Leaning Tower of Pisa. Newton famously performed equivalence principle tests when he was developing his Principia Mathematica and his theory of gravity. These days, the most precise tests of the equivalence principle are performed in space by the microscope experiment, constraining violations of the equivalence principle down to 1 part in 10 to the 15. Another class of tests are tests of the inverse square law. These leverage the fact that the force mediated by gravity and the force mediated by the scalar have different ranges. In particular, gravity is infinite range, but as you move into and out of the range of the fifth force mediated by the scalar, the strength of the force between two test masses grows by a factor of alpha 5. And this has been used to constrain new interactions over a huge range of scales. In particular, we know that gravity is the dominant force over ranges between about 50 microns and the size of the observable universe, down to 1 part in 1,000. And in some parts, the constraints are much, much stronger, down to 1 part in 10 to the 10. But at shorter distances and weaker couplings, a new force could be hiding out there. Now, in order to talk about these couplings more precisely from a particle physics perspective, we want to write down a particular interaction between the scalar and the standard model particles. Take, for instance, the scalar interaction with the electron. Here, kappa is the inverse Planck mass, and DME is dimensionless coupling. When we compute this interaction, we are left with the Yukawa potential, whose strength is gravitational strength if DME is equal to 1. In terms of these parameters, we can write down constraints. On the vertical axis, we have DME. On the horizontal axis, we have the scalar mass. And we can see that equivalence principle tests and fifth force tests constrain the strength of these interactions to be subgravitational over a huge range of scalar masses. Now, the scalar field is not just a mediator of fifth forces. Much like gravity can have a relic abundance as gravitational waves, the scalar field can have a relic abundance as well. But the scalar field will have a mass and therefore can constitute some fraction of the dark matter. Now, the simplest production mechanism for scalar particles is the misalignment mechanism, and this takes place during inflation. So here is the scalar potential versus the scalar field. Now, during inflation, the scalar field is stretched and flattened so that everywhere in the universe, it acquires a single homogeneous expectation value. But because of inflationary fluctuations, this expectation value can take a random walk. And so generically, it will be displaced from the vacuum expectation value. This initial misalignment then begins diluting like cold matter once the Hubble rate of the universe drops below the mass of the scalar, well into the radiation-dominated epoch. This relic abundance scales with the mass of the scalar to the 1/2 power and the initial misalignment squared. Now, if the scalar field constitutes some fraction of the dark matter, then today in the galaxy, the scalar field behaves as a coherent classical field. The magnitude of the field is given by the local energy density of the scalar field, and its frequency is given by the mass of the scalar field. In the background of these scalar fields, standard model particles acquire oscillating fundamental constants, for example, the electron mass. The easiest way to see this is by looking at the fifth force diagram and cutting it in half, pinning on the scalar field background, and immediately we can read off that the mass of the electron becomes a function of the scalar field. If the scalar field constitutes all of the dark matter, we get an additional handle with which to probe this parameter space. In particular, down at the lower mass regime, nanograv, pulsar timing arrays rather, in general, but nanograv in particular, and atomic clocks are able to probe these oscillations of the electron mass to high precision, placing stronger bounds on the parameter space. At higher frequencies, laser interferometers such as LIGO and GEO 600, as well as resonant masses, can place constraints as well. In the future, atom interferometry and atomic clocks will place much stronger constraints or detect these new scalars over a large swath of parameter space. Now, the scalar electron coupling is just one of several ways in which a scalar can couple to the standard model that would be observable at lab energies. This includes the scalar photon coupling, which would show up as an oscillating fine structure constant, the scalar gluon coupling, which shows up as oscillating nucleon masses, and the scalar quark coupling, which also shows up as oscillating nucleon masses, but suppressed by the quark mass relative to lambda QCD. In the rest of the talk, I'm going to discuss how scalars interact with standard model plasma, and how this leads to a relic abundance for the scalar field that relates the relic abundance to the coupling to the standard model. I'll then discuss how this relic abundance is fairly universal because of the particular structure of the standard model. Now, in the early universe, when the standard model was very hot and very dense, the scalar field will acquire an effective potential. And because the early universe was quite homogeneous, this effective potential is just given by minus the pressure of the standard model, where the fundamental constants of the standard model of degrees of freedom are replaced by their field-dependent values. Now, I don't have to remind this audience that pressure is a measure of force per area time average imparted onto the barrier of a container. So here is my box of electrons and positrons. I'm going to imagine that their mass and couplings to the photon are 0 for the moment, so that their pressure is just given by dimensional analysis, temperature to the fourth, up to phase space and degrees of freedom counting. As we turn up the electron mass, what happens to the pressure? Well, the energy per particle is fixed. That's the temperature. But as we increase the mass, the momentum per particle has to decrease, and so too must the force onto the barrier, which is proportional to the momentum. Therefore, the pressure decreases in the presence of a non-zero electron mass. And in the high temperature limit, the leading order correction is m squared t squared. Therefore, the scalar field acquires an effective potential that scales as the electron mass squared times temperature squared. This effective potential generically will displace the scalar field from its vacuum expectation value in the early universe, so that even if the scalar field started with 0 energy density, it will acquire energy density due to this effective potential that will lead to a misalignment production later in the universe. If the scalar field couples to photons, a similar story happens. We can reason about it in a similar way to how we reasoned about the pressure due to the electron coupling. In the absence of the fine structure constant and the electron masses, the pressure of my electron-positron plasma is given by dimensional analysis, T to the 4. But as we turn on the fine structure constant, the interactions between the electrons, positrons, and photons leads to the emergence of plasma masses for all of these particles. Now, just like the bare electron mass suppressed the momentum of these particles at fixed energy, the temperature, so too will a plasma mass. But this time, the only scale in the problem is the temperature. And so ultimately, the pressure is suppressed by E squared T to the 4. So the scalar field, if it couples to the fine structure constant, will feel an effective potential that goes as E squared T to the 4. And importantly, because the scalar field coupled to a dimensionless parameter, the effective potential at high temperature is much larger. This is a key result for our work. So how does this relate to the structure of the standard model? Well, the standard model consists of many mass scales. You have the electrons, you even have the masses of elements. But you have the electrons, the up quark, the down quark, the strange quark, the muon, charm, tau, bottom, the WZ, and you also have the QCD scale and the electroweak scale. But as you go towards higher temperature, all of these scales to which the scalar field might couple are replaced by dimensionless couplings. For instance, when the universe was hotter than the QCD scale was replaced by the dimensionless SU3 gauge coupling, G3. Above the electroweak scale, the lepton and quark masses are replaced by lepton and quark Yukawas, and the W and Z masses are replaced by the U1 hypercharge and SU2 gauge couplings. So that above the electroweak scale, the only dimensionful parameter in the standard model that remains is the mass of the Higgs, or rather the Higgs mass parameter, the negative Higgs mass parameter that is physical above the electroweak scale. So to summarize that story, dimensionful parameters are replaced by dimensionless ones at higher energies. So for a given set of scalar couplings at t equals 0, be that two dimensionful couplings or dimensionless ones, the effective potential of the scalar field at high temperature is given almost always by a dimensionless coupling squared times temperature to the 4th, which scales very rapidly with high temperature and can lead to very efficient production of the scalar field. And as we will see on the following slides, this leads to a nearly universal prediction that the relic abundance of the scalar field matches that of the dark matter if the scalar field coupling to matter is 10 to the minus 6 times the mass of the scalar field in units of electron volts to the minus 1/4 relative to gravity, with little dependence on x. What this means is little dependence on what particle the scalar field couples to. This result only depends on the strength of the coupling. So here I have a plot of the scalar field coupling to the electron mass. On the horizontal axis, again, I have the scalar field mass. And these red regions are the prospective sensitivity curves of future experiments, and these gray regions are excluded. These colored lines represent our prediction for the coupling of the scalar field to the standard model that yields the correct dark matter relic abundance for different reheat histories of the universe. Blue lines are colder reheat temperatures. Red lines are hotter reheat temperatures. This line is reheating the minimum reheating temperature up to BBN. This is reheating up to the QCD phase transition, and this is reheating up to the electroweak phase transition. And what we see is that light scalars are very insensitive to the reheat temperature, so long as the reheat temperature was sufficiently high. On the other hand, heavy scalars are fairly sensitive to this reheat temperature. But as the universe reheats to a hotter and hotter temperature, we approach this prediction that I mentioned on the previous slide. Similarly for coupling to photons, and similarly for coupling to gluons, so long as the universe reheats above the QCD phase transition, the scalar field couplings end up on this same line. There is one exception. If the scalar field couples to the Higgs mass parameter above the electroweak phase transition, then this line is cut off at the electroweak phase transition. But nonetheless, at lower scalar masses, this line still persists. In particular, as long as the scalar field mass is smaller than the Hubble rate at the electroweak phase transition, which is 10 to the minus 5 electron volts. In fact, in this particular scenario, we get additional information. The ratio of the couplings of the scalar to the standard model at low energies are fixed in terms of the coupling at high energies. Now, there are some limitations to this prediction. We might worry about the breakdown of perturbation theory, scalar self-interactions, whether these interactions can be natural, the role of isocurvature perturbations, and whether other production channels might dominate. I don't have time to go over these in detail. Suffice it to say that self-interactions in the typical part of parameter space often do not play a significant role, although they can if they're quite large. The non-perturbative behavior of the scalar field is a concern, but not on our predicted line. Thermal production is often negligible, and inflationary production is also often negligible. The most significant constraint is isocurvature, and I encourage you to go back and look at the previous slides, where you can see isocurvature constraints as dashed lines. Naturalness is also a concern, but under fairly conservative assumptions, it also does not play a role, at least on the lower right edge of our predictions. So in conclusion, interactions mediated by scalar fields at lab energies are connected to scalar cosmology. And in particular, because scalar couplings mix, owing to the running of the gauge couplings, dimensional transmutation, and spontaneous symmetry breaking, the scalar will almost always couple to a dimensionless parameter in the UV, leading to an effective potential that scales as temperature to the fourth, independent of what particle the scalar couples to at low energies, with one exception. Leading to the prediction that the correct dark matter abundance is achieved for the scalar field if it is coupled to the standard model with this particular strength relative to gravity, leading to a sharp prediction for future experiments targeting scalar dark matter. Thank you.